In this video, we will be looking at the double angle formulas. And before we look at the actual formulas, we're going to prove them using our knowledge of compound angle formulas. So we're going to start off by proving the double angle formula for sine of 2a. And sine of 2a really just means sine of a plus a, because a plus a is 2a. And now we can use our compound angle formula. So we're going to have sine A cos A plus cos A sine A. These are like terms. They both have a sine A and a cos A attached by multiplication. So we can simplify this to sine A times cos A. And there's our first double angle formula. Let's go to cos. Cos of 2a is just cos of a plus a. Using our compound angle formula, that's going to be cos a times cos a minus sine a times sine a. If we clean that, that is just cos squared a minus sine squared a. And there's the first double angle formula for cos. Now, cos has two other options, and it does come from a combination of the first double angle formula and Pythagorean identity. So as a reminder, our Pythagorean identity is sine squared x. I'll just use a to match the a's that we have here. So sine squared a plus cos squared a equals 1. And we know that we can rearrange the Pythagorean identity into sine squared a equals 1 minus cos squared a, and that cos squared a equals 1 minus sine squared a. So I'm going to use both options in our double angle formula. So one version, I'm going to replace sine squared a with 1 minus cos squared a. So me bringing the cos squared a over in the Pythagorean identity and then subbing that in. And now if we clean this up, we'll have cos squared a minus 1 plus cos squared a. And if we collect, that's 2 cos squared a's subtract 1. There's an alternate double angle formula for cos. I'm going to put the other one right over here. So instead of replacing sine squared a for the second option, I'll replace cos squared a with 1 minus sine squared a. So there it is. And this, when we collect, is just going to be 1 minus 2 sine squared a's. And there's the other version of the double angle formula for cosine. So it is just all starting from this, and then we can get the other two options when we combine our double angle formula with our Pythagorean identity. And finally, our tangent double angle formula. So that's going to be tan a plus a. And if we use our compound angle formula, that would be tan a plus tan a all over 1 minus tan a times tan a. This simplifies to 2 tan a's in the numerator and 1 minus tan squared a in the denominator. And there's our tangent double angle formula. So now let's try using these double angle formulas for some questions. All right, we're going to express each of the following as a single trig ratio, and it's going to involve us looking at each expression and determining which double angle formula it represents. So for A, we see 2 times sine x times cos x. Well, that's our sine double angle formula. So this is just equal to sine of 2x. For the next one, we have 1 minus 2 sine squared of 8x. This looks like our cos double angle formula that says cos of, let's say, 2 theta equals 1 minus 2 sine squared theta. But instead of theta, we have 8x. So it's going to be cos of 2 times 8x, which means this is just equal to cos of 16x. All right, for C, we have 2 times tan of 3x all over 1 minus tan squared of 3x. This is your double angle formula for tan, but here our theta is 3x, which means we're going to have tan of 2 times 3x, which is tan of 6x. The next one, express the following as a single trigonometric ratio and then evaluate the exact value. Cos squared of pi over 12 minus sine squared of pi over 12. Now, pi over 12 is not one of our special triangle angles, so if I tried to use it, I would not be able to get an exact value. However, when I see this cos squared of an angle minus sine squared of an angle, it reminds me of the double angle formula for cos. But instead of x, it's pi over 12. So this is equivalent to cos of 2 times pi over 12. And if I clean up that angle, this would be 2 pi over 12, which reduces to pi over 6. Well, pi over 6, I have no problem. I can draw my special triangle. Pi over 6 is over here. It's the 30 degree. And cos of pi over 6 is root 3 over 2. And that is an exact value because I was able to simplify this into a double angle formula, and the angle, when cleaned up, became a special triangle angle. All right, next, use a double angle formula to rewrite each trig ratio. Okay, well, if I have sine of 4x, that's not really a double angle formula, but I can make it one by writing sine of 2 times 2x. So I'm doubling 2x. 2x would be my angle. So this is going to be 2 times sine of the angle times cos of the angle that's being doubled. 2x was being doubled. Here it is. Next, we have cos x. How can we write that as a double angle? Well, we're doubling 1/2 x. 1/2 x is going to be our angle. And with the cos double angle formula, we have 3 variations. I'm just going to use the original one. So cos squared of 1/2 x, but I'm just going to write it as x over 2, minus sine squared of x over 2. Next, tan of x over 4. What are we doubling to get x over 4? Well, we could be multiplying this by x over 8 because 2 over 8 is a quarter, so here we are. And now we can use our double angle formula. 2 times tan of the angle that's being doubled, so tan of x over 8, all over 1 minus tan squared of the angle. So now let's try another style of question. Determine the values of sine of 2 theta, cos of 2 theta, and tan of 2 theta, given that tan theta equals negative 7 over 24, and theta is between pi over 2 and pi. That puts us in quadrant 2. So I am going to start off by drawing a diagram for myself here. So here's theta. There's my terminal arm in quadrant 2. And I'm just going to create a triangle out of this. We know tan is opposite over adjacent, which means opposite to our angle, we should have 7, and adjacent is 24. Now that negative, logically looking at the quadrant we're in, should go with the 24, because 24 is on the negative x-axis. 7 is on the positive y-axis. If I want to find the values, the exact values of sine, cosine, tan of the double angle, I do need to make sure I know sine, cosine, tan of theta first. And I know tan, but I need sine and cos as well, which means I need my hypotenuse. So I'm just going to do a little Pythagorean theorem here. So 7 squared plus negative 24 squared equals r squared, r for the radius of the circle that would be created by this terminal arm. 7 squared plus negative 24 all squared is 625. And when we square root both sides, we get plus or minus 25 for that hypotenuse. And the radius or the length of that terminal arm will always be positive, no matter what, because it represents the radius of the circle, and that's an actual dimension, which is positive. Now I know that sine theta equals opposite over hypotenuse, there it is, and cos theta equals adjacent over hypotenuse, there it is. Now I'm ready to go with each of the double angle formulas. So sine of 2 theta equals 2 sine theta times cos theta. Well, now we know that sine theta equals 7 over 25 and cos theta equals negative 24 over 25. And now let's just multiply. And remember, if you need to, put the 2 over 1. So 2 times 7 times negative 24 is negative 336. And then 1 times 25 times 25 is 625. So there's sine of 2 theta. Cos of 2 theta is going to be cos squared theta minus sine squared theta, or one of the other variations would work as well. So that's going to be negative 24 over 25 squared minus 7 over 25 all squared, which is 576 over 625. Remember, you're raising the numerator and denominator to the power of 2, minus 49 over 625. And we have a common denominator, so we can subtract. And we get 527 over 625. And finally, tan of 2 theta. Now, there is a very simple way to find this, a lot faster than I'm going to do in this video, which is if I already know what sine and cos are equal to, and we know that tan is sine over cos, I can do sine of 2 theta divided by cos of 2 theta and get my ratio within a step. But I do want to practice using the double angle formula for tan, so I am going to go the long way. That way we're also practicing our fraction skills. So we're going to do 2 times tan theta over 1 minus tan squared theta. So we have 2 times negative 7 over 24 all over 1 minus negative 7 over 24 all squared. Now I see I'm going to have fractions within fractions, so I'm going to turn this main fraction line into division in my next step. So I'll do the multiplication here. 2 times negative 7 is negative 14, and then over 24. And that's going to be divided by the denominator. And since the denominator isn't a united fraction yet, I'm going to put it in a bracket until I can unite it. So we have 1 minus 49 over 576 when we apply that exponent of 2. And I'll get a common denominator for that 1. It's going to be 576 over 576. And when we simplify that, that would be 527 over 576. And then for the first numerator, I left it blank just because I wanted to reduce the fraction. And now we know division turns into multiplication if we reciprocal the second fraction. And now if we do the multiplication here, we first get negative 4,032 over 6,324. And if you reduce that, that gives us negative 336 over 527. All right, let's go to our next example. Ari needs to find the exact value of sine of pi over 8, and he knows that cos of pi over 4 is 1 over root 2. How can he use this fact to answer this question without using a calculator, and what is the correct answer? So I need to use a double angle formula here that has sine and cos in it, where one's a double angle and one ratio is not for a double angle. And that makes me think of the cos double angle formula. So I'm going to say cos of 2x is equal to, and I'm not going to use the original one. I'm going to use one of the rearranged Pythagorean identity ones, which is 1 minus 2 times sine squared x. And instead of x, I'm going to replace it with pi over 8. That way, I'll get sine of pi over 8 here, but squared. And then when I do 2 times pi over 8, I'll get the pi over 4 from the exact ratio that was given to us. So cos of 2 times pi over 8 equals 1 minus 2 sine squared of pi over 8. Clean this up. So that's cos of pi over 4 equals 1 minus 2 sine squared of pi over 8. And now I'm just going to start rearranging because I want to try to isolate for sine of pi over 8 because that's the goal. And I'll also replace cos pi over 4 at some point with that 1 over root 2. But what I'm going to do, I'm just going to do a little swap here. So 2 sine squared of pi over 8 equals 1 minus cos pi over 4. We can bring in the ratio anytime. We can finish isolating first or bring it in first. It doesn't matter. We'll get to the same place. I'm just going to start swapping in that ratio. But when I swap it in, I'm not going to write 1 over root 2. I'm going to write root 2 over 2. And then I'll get myself a common denominator. So instead of 1, we can write 2 over 2 and unite those fractions before we start isolating for sine of pi over 8. So I'll just come up here. And to get rid of that 2, I'm going to multiply both sides by a half. And when I do that, that will make my denominator 4. And the numerator will not change. And now finally, we can square root both sides to get rid of that exponent of 2. And that way, we've isolated for sine of pi over 8. Now, when I square root both sides, I'm going to remember my plus or minus. And also remember, when you square root a fraction, you're squaring the numerator and the denominator. Well, the square root of 4 for the denominator is just 2, so I will just evaluate that. But in my numerator, I can't really clean that up. And I do have a radical within a radical, and that's fine. But now we have an exact ratio for sine of pi over 8. And without the use of this double angle formula, we wouldn't have had an exact value. Now let's use our double angles for some trig identities. So let's start with A. Sine squared x minus 1 all to the power of 2 is equal to cos of 2x plus sine of sine 4x, or sine to the power of 4x. So we want to start with the more complicated side. I'm going to pick the right side because I do see a double angle that I can try to simplify. Now when I look at my goal is all about sine. So I'm going to replace the double angle of cos with the variation that is all about sine. 1 minus 2 sine squared x, and then plus sine x all to the power 4. And when I see this, I see it as a trinomial, but I want to put it in proper form. So highest exponent first, then the next one, then the constant. And when I rearranged it, I made sure to keep the signs of the terms the same as the original line. And now I can factor this. So sine squared x times sine squared x is sine to the power of 4x. And then 1 times 1 is 1. But if I want my check to work, I should make them both negative. That way I have negative sine squared x and negative sine squared x, which does give us that negative 2 sine squared x from the middle. So that's just going to be sine squared x minus 1 all squared, and that's exactly what the left side is. So therefore, left side equals right side, QED. That which you wanted me to prove, I have proven. So, concluded. All right, let's try our next one. Cotangent x minus tangent x equals 2 cotangent of 2x. I'm going to start with the right side because I think there's more to do with the double angle. Now, I'm going to replace cotangent with the identity of cos over sine. So cos of 2x over sine of 2x. And then I'll rewrite each of those double angles with one of the appropriate formulas. So for cos of 2x, I'm going to write the original cos squared x minus sine squared x and see if that gets us anywhere. And instead of sine of 2x, I'll write 2 sine x cos x. And then from here, I notice that the 2's can cancel out, and I'm left with cos squared x minus sine squared x all over sine x cos x. And then I'm going to split this off into two fractions. So I'm kind of going to undo the common denominator here. So that's going to be cos squared x over sine x cos x minus sine squared x over sine x cos x. Because if you would see this, normally you would just simplify this into cos squared x minus sine squared x over that common denominator. But now when I see it like this, I can bring those two terms. So first of all, the first fraction, a cos in the numerator can cancel out with the denominator cos, and that leaves us with cos x over tan x, which is cotangent x. And then in the second fraction, one of the signs in the numerator can cancel out with the sine x in the denominator, and that leaves us with sine x over cos x, which is tan x. And that was the left side. So therefore, left side equals right side. And because we do have sine and cos in the denominator at one point, we do need some restrictions for this one here. We can't have sine x that equals 0 and cos x cannot equal 0. So I'm just going to draw our little base functions here. And when we look at this, when is sine x equal to 0? At 0, at pi, at 2 pi, pretty much every multiple of pi. So x cannot equal n times pi, where n is an integer. And for cos, the restriction would be for pi over 2, 3 pi over 2, and so on. So x cannot equal pi plus 2 pi n all over 2 NEZ. These would be two separate restrictions, but if we can unite it, that would be best. So I'm just going to cross those out, but that's just a good reminder if you had those individual restrictions, what they would be. Now, if I look at sine and cos, when each of them is equal to 0, we are at 0, at pi over 2, at pi, at 3 pi over 2, at 2 pi, and so on. And as a reminder, pi is just 2 pi over 2, 2 pi is 4 pi over 2. So if you look, it's just the coefficient of pi that is changing for a common restriction. So x cannot equal n times pi over 2, where n is an integer. That way we could have 1 pi over 2, 2 pi over 2, 3 pi over 2, negative 5 pi over 2, and that would include all of the restrictions for both sine and cos. All right, let's go to C. For C, it said sine of 2 theta over 1 plus cos of 2 theta equals tan theta. And here, the left side is definitely the more complicated side. So I'm going to start with that. And I'm going to replace sine 2 theta with 2 sine theta cos theta. And for the cos 2 theta, I'm going to replace it with the one just related to cos, because I'm hoping some things will cancel out so that I get tan. I also know that tan is sine over cos, so having just cos in the denominator might be helpful. That's my logic behind that choice. And now let's clean up. We'll have 1 plus 2 cos squared theta minus 1. The 1's cancel out, and we're just left with 2 cos squared theta. But then the 2's cancel out, and a set of coses cancel out. So then we're just left with sine over cos, which is tan theta. So the left side and the right side are equal to each other. But we're going to have a restriction here because we have cos squared theta in the denominator. So cos theta cannot equal 0. So theta cannot equal pi plus 2 pi n over 2 and ez. And that's again from the base function, pi over 2, 3 pi over 2, 5 pi over 2, and so on are the values when cos would be 0, which we can't have. And let's go to our last identity, which said sine of 3x equals 3 sine x cos squared x minus sine cubed x. I'm going to start with my left side. I know it doesn't look as complicated as the right side, but I have a potential to use one of the double angle formulas. However, 3x isn't doubling. So how can I start this off? Well, I can write 3x as x plus 2x, which is going to allow me to use the compound angle formula and then a double angle formula later. So the compound angle formula for sine x times cos of 2x plus cos x times sine of 2x. And now I have two double angle formulas to replace. So instead of cos of 2x, I'll write cos squared x minus sine squared x. And then instead of sine of 2x, I'll write 2 sine x cos x. And let's clean this up and see what happens. So if I distribute here, I'll have sine x times cos squared x, which is good because I wanted that. And sine x times sine squared x is sine cubed x, so that's great. And then when we clean up this multiplication, it's going to be 2 times sine x and then cos squared x. And now these can collect, and we'll get that right side. So therefore the left side equals the right side, and there are no restrictions here because we didn't have any denominators.